This is Chapter 6 on Discrete Probability Distributions. So it's an extension of Chapter 5, still remembering everything we learned about probability, and then turning it into or applying it to discrete distributions. So the first thing I want to talk about is what a random variable is, a discrete random variable. So a random variable is a numerical measure of an outcome of a probability experiment. So it's the variables we collect that happen by chance. And so its value is determined by chance, and we use capital letters to denote a random variable. And the most common random variable is capital letter X. So an easy example of this is flipping a coin. If I flip a coin twice and count the number of heads, what are all the possible values of X? X could be 0, X could be 1, or X could be 2. If I flip a coin twice, I could get 0 heads, that's a random variable. I could get 1 head and 1 tail, or they could both be heads. So all my outcomes are 0, or 1, or 2. Same idea, if I flip a coin 5 times and count the number of heads, what are all the possible values of X? I could still get 0, or 1, or 2, or 3, or 4, or 5, and that's it. The most I can get is 5 heads if I flip a coin 5 times. The one that students often forget is 0. So remember that 0 is always a possibility for a random variable. Could happen 0 times. I can get 0 successes out of however many trials I'm doing. So another example, if I measure the time between cars at an intersection with a stopwatch. So between cars. So one car passes, I start the timer, and I wait until the next car passes and stop the timer. What are all the possible values of X? Here it's not so easy to just list all of our options. Here, X can be any number greater than 0. Who knows what kind of times I'm going to get? I could be sitting there for just a few seconds, I could be sitting there for hours. And the time is a continuous measurement that could take on any value greater than 0. So that creates 2 types of random variables. The first one is a discrete random variable, just like Chapter 1. And this can be counted, again, very similar to the Chapter 1 examples. This can be counted and has a finite number of outcomes. So there's only certain numbers you can get, and that's it. Continuous random variables have infinitely many values and are usually generated from measuring. So usually generated from measured values. So Chapter 6 is all about discrete random variables, and Chapter 7 is about continuous random variables. So we're going to talk about each one separately. So let's talk about a little bit more about the difference between discrete and continuous. So with each of these 4 examples, decide if it's discrete or continuous and what are the possible values for X. So Part A wants to know the number of students who got an A on the exam. X could be 0, no one got an A, could be 1, could be 2, all the way up to what we call N, which in this example would be the class size. So if I have 24 students, I could have up to 24 A's. If I have 30 students, I could have up to 30 A's. That is a discrete measurement because I'm counting the number of students who got an A. On Part B, it's the speed of the next car that passes through the intersection, so I'm measuring the speed, which makes it a continuous random variable. And X could be any number greater than 0. So if the car is driving, it could be any speed greater than 0. Part C, the number of light bulbs that burn out next week in a building with 20 light bulbs. So again, it's a number we're counting. So that's discrete. And X could be 0, it could be 1, it could be 2, all the way up to the limit of 20. So there's 20 light bulbs, no more than 20 of them can go out. And the last example, the time it takes for a light bulb to burn out. Time is a measurement, so that is a continuous distribution, and x could be any number greater than 0. So if I have a timer set on each bulb trying to measure how long it's good for, that's a continuous measurement. So again, we're focusing on discrete for Chapter 6. We'll get into continuous in Chapter 7. So for discrete probability distributions, we've seen probability distributions before. And this is trying to kind of list out all your options and their corresponding probabilities. So this is a table of all the possible values for x and the probability of each one occurring. So we've seen this before. Just like other frequency distributions, all probabilities, which are relative frequencies, must be between 0 and 1, and they also must sum to 1, which again represents 100%. So let's look at these three examples at the bottom. Are these three valid probability distributions? So if we look at the first one, this last probability is negative, so that's an automatic no. If we look at the second one and we start to add them up, they sum to more than 1. So the sum is greater than 1, so that's not a good model. If we look at the last one, all of the values are between 0 and 1, and if you add them up, they do add to exactly 1. So part C is a valid probability model. So we're going to see this, all the outcomes for x and their corresponding probabilities. We're also going to learn how to calculate all of these probabilities given different situations. So in my face-to-face class, we run a little bit of an experiment called the paper football challenge. So we're just going to kind of pretend like we're doing this. And I have the students fold up a little paper football, and they flick the football into what we call a field goal. And they count up how many field goals they get out of 5. So the first student goes, they flick their football 5 times. Let's say they got 2 out of 5 field goals. Then they go again, and let's say they get 3 out of 5 field goals. They go again, and they only got 1 out of 5 field goals. So what they're doing each time is flicking the football a set number of times, let's say 5, and they're counting up how many successes they got out of 5 for a various number of trials. So I'm just going to kind of make up some data here. Let's say they got no goals there. Let's say they did really good on trial 7, 3 on trial 8, 2 on trial 9, and let's say 1 on trial 10. So they never got 5 out of 5, but they did pretty good. So if you have this data of how many successes you got for each trial, what we're going to do now is gather up the frequency of each of the possible outcomes. So if I'm flicking the paper football 5 times, I could get 0 successes, 1, 2, 3, 4, or 5 successes. So this is an empirical probability technique. We're going to run this experiment. We're going to count up how many times did we get 0, just once. How many times did we get 1? Looks like 3 times. How many times did we get 2? Looks like 3 times. How many times did we get 3? Got 3 twice. We got 4 once, and we never got 5, and that's okay. So it's okay for a frequency to be 0. Now from this, we know we flicked the football 10 total trials. So my relative frequency is going to be 1 divided by 10, 3 divided by 10, 3 again divided by 10, 2 divided by 10, 1 divided by 10, and 0 divided by 10. If I add up all my relative frequencies, they add to 1, which represents 100% of the data. So normally, you're given your different x values, this first column, Generally speaking, they don't give you the frequency, they just go right ahead and give you the relative frequency. So these are the two columns we're going to focus on: the different outcomes and the probability of them occurring. The frequency is just used to help you get relative frequency. So we're going to create a discrete histogram for our data. You have the numbers 0 through 5 along the bottom, centered between each mark. The relative frequency for 0 was 0.1, so we'll make that bar. The relative frequency for 1 is 0.3. Then we got 0.3 again for 2. For 3, our relative frequency was 0.2. And for 4, it was 1, and we did not have any outcome of 5. So in my class, everyone has different numbers up here and we all get different data, but we're just going to use the same data here to keep it consistent. So you have all your outcomes and how often they occurred, their relative frequency. In order to get the average for a probability distribution, each outcome is kind of weighted. It's kind of like your average in the class. So this percent is this percent is that. So it's kind of like a weighted average. And so in order to do this, you have to multiply the random variable by the probability of it occurring. And again, it's kind of like a weighted average where each part of your average has a different percentage weight. Once you multiply them, then you sum all of those outcomes. So what I'd like you to do is copy over your relative frequency into this chart. 0.1, 0.3, 0.3 again, 0.2, 0.1, and 0. On your homework, this is what you're going to be given: the x values and their corresponding probabilities. So you'll just see a little 2-column chart on your homework. I added this third column to help us find the mean, so that's just a working column to help you out. So what I'd like you to do is multiply each x value times its probability and put the product in that third column that I created. Multiply, multiply, multiply. This is the same way, like I said, same way you would get your average if each category had a different percentage weight. So you multiply each one out. That's your weighted. Then you're going to add all those up. So we're going to, remember this capital sigma means sum. We're going to sum these products. So 0 plus 0.3 plus 0.6, 0.6 again plus 0.4 plus 0. So you add them all up. I got 1.9. And that is my average or mean. So it's a different way of calculating the mean, and that's because each outcome has a different frequency or relative frequency. So if you look on your formula chart in Chapter 6, the first thing you see is the mean, which is called an expected value. I'll explain that here in a minute. For a discrete random variable, which is what we're studying right now, is the sum of each x value times its probability. So that's what we just did. We took the sum of each x value times its probability. So we call this an expected value. We use the mean of a discrete random variable to represent the expected outcome for the random chance event. So in this example, I flicked the paper football 5 times. So I'm saying out of 5 times, given these results, out of 5 times, I'm expecting to make 1.9 field goals. And if you're into sports statistics, they do this all the time. They take the players' statistics and they come up with this expected value, their expected amount of success out of however many they're measuring. So if I was a paper football player, they would say that my expected field goal success would be 1.9 out of 5. So that's what we call an expected outcome. It's what we're expecting to happen each time. So your paper football challenge statistics would be an average of 1.9 out of 5 attempts in the long run. So when you see expected value, just think average, and this is how we get the average. Now for standard deviation, we always have mean and standard deviation. They go hand in hand. When we go to get the standard deviation, we're going to let the calculator do this for us. I don't expect you to understand how to do this by hand. So you'll see here, standard deviation for a discrete random variable. You can cross all that fun stuff out and just write calculator. And actually the calculator can do this one for you as well. I'll show you that. This one's a little easier to do by hand. This one's much more challenging. So I'm going to show you in the calculator how to get the mean and standard deviation for a discrete random variable. Alright, first thing we're going to do is go to our calculator. I'll get my old one as well. So old or new. You want to go to Stat, Edit. Whatever's in there, clear it out. So go to the top, push Clear, Enter. Go over to the top, push Clear, Enter. Never, ever, ever push Delete on a list. You should have your L1 and L2 at all times. So in L1, we're going to put our x values, and in L2, we're going to put the probability of each one of them occurring. So 0, 1, 2, 3, 4, 5, and their corresponding probabilities right next to them. And make sure they line up just like in chapter 4. So same thing on the older calculator. Go to that over, 0.1, 0.3, 0.3. Make sure your decimals get in there. Sometimes we go too fast and we miss the decimal. So L1 should be all your outcomes. Sorry about the glare. And L2 should be your probabilities of each outcome. This last column, remember, is not part of it. That was just used to help you calculate by hand. From here, this is a little different. You're going to go to Stat, over to Calculate. We're going to choose one of our stats again, which we used back in chapter 3. So hit Enter for one of our stats. If you have a newer calculator, it waits for you. If you have an older calculator, it's tempting to just hit Enter again. In that glare. There we go. So in the newer calculator, it asks you for the list and the frequency list. The frequency list is where L2 is. L2 is the weight for each category, or for each outcome. So if you push second 2, you can see a little L2 above 2. Hit second 2 for L2, and then go down to calculate. In an older calculator, it's harder. You have to remember for this section, we put L1, comma, L2. So you hit second 1 for L1, and then the comma, which is above the 7, and then second 2 for L2. On the older calculators, it's very important to remember this. If I have data in L1 and L2, and the L2 is your probabilities, you have to put that in there. If you did this correctly, your x bar 1.9 should match the one we got by hand, 1.9. And then your standard deviation is here. So standard deviation of x is 1.357, or 1.1357. So you'll see it here. So just make sure your x bar is correct. Again, when you have data in L1 and L2, you have to tell the calculator to use both to get a weighted average. So our standard deviation should be 1.136, and the homework will tell you how to round, but you want to make sure you know how to get that. These steps are for the older calculator where you have to remember L1, L2. That's the part that students forget. Newer calculators, it's a little easier because it kind of prompts you for it. All right, let's see where we're at. So that is random variables, specifically discrete random variables, how they correspond with their relative frequencies. We can always graph them, how to get the mean, and the standard deviation. I'm going to go ahead and stop there, and then I'll start 6.2 on its own video.